today's lecture, I have taken very simple things, or we can say it as what are the basic things one can must know while identifying the minerals. Because in most of the times, what we do is we go on classifying the Rasadravya according to our Maharasa, Uparasa, Sadharan Rasa. Then one group of Maharasa belongs to one group of mineral, and second drug immediately changes and it will belongs to other group of mineral, so that students will not keep a tempo not how to understand these minerals. So that even though it is simpler if we classify according to mineralogical classifications, but when we teach according to our Maharasa, Uparasa, Sadhan Rasa, Ratna Varga Dravyas, the each and every mineral will not fall into the modern mineralogical classification of the drugs. So the tempo will change, and that simple thing will make the topic a little bit more difficult to understand because of the shifting of the group of the minerals in our classification. So today's class, I have planned to share with all the postgraduate scholars is to classify the minerals according to the different classifications, and we can understand each and every mineral group little bit, so that it will help in understanding, or it will help in identifying the our rasadravyas. So, with the blessings of the Lord Dhanvantari, and gratitude to the Amrita School of Ayurveda for providing me opportunity, we will start with the today's topic. Thank you so much, sir.
Thank you, sir. Now I invite Dr.
Whether my screen is visible?
Yes, sir. Yes, sir. Yes, sir.
Yes, sir. Display.
Okay. I'm not able to change my slides. Is there any difficulty?
Sir, can you share again that?
1 second, sir.
And share.
Now is it changing?
Yeah. Yes.
Yes. Okay. So, before going to start, actually, the understanding of the minerals and metals in Ayurveda, why we need to study minerals and metals? So, we have already established castosities, there are Rasadravya, there are so many potent medicines are available in the castosity section. So, why we need to study the minerals, or why we need to have the minerals and metals in Rasashastra, or in medicine, or Ayurveda medicines? The basic principle, as we all know, is that in the Rasarnava text, when there is a samvada between Parvati and Shiva. So, during the discussion, the Parvati asks about what is the real salvation or real moksha. So, in that question, Shiva replies to Parvati with shloka Pindapate yecha moksho sacha moksho nirartakaha pindetu patite devi ghardabhoyapi vimachate. So, he explains that if you consider our body as a death, or the moksha, then even Gardaba or all the animals who will die one or the other day, they all get moksha then. Then Parvati asks, what is the real moksha? Then he put forth the theory of Sadeha moksha. So Sadeha moksha, if you want to attain the Sadeha moksha, then it is not possible with the Kashtav, because even the Rasaratna Samuchaya, the Acharyas have clearly explained about the fragile nature of the Kashtav. Dahyam, Kledyam, Sosham cha. If you put the Kashtav in a fire, what will happen? They will be burnt out. And if you put our Kashtav in water, they will be putrefied. And if we put our Kashtav for a long period, they will be shoshan. There will not be any therapeutic properties being left. So then we need something, something material, or some material which can possess, or which give the stability for the Sadrada Sharira, because we want to make moksha with the maintaining the Dhrada Sharira, and with Sadeha Moksha, we want to achieve the ultimate salvation according to the Rasa Acharyas or Rasa Siddhas. So for that, they have rejected these caste aushadhis because, as I explained about their fragile nature, that is Dahya, Kledya, and Sosha. So the contrastingly look into our medicines, Rasadravyas, how they are. When you put into water, they will be purification. When you put into the fire, they are converted into more assimilable form basmas. And when you keep it for long duration, there is no shoshana. Their therapeutic potential will be increased. So rightly, when you look into the Rasatna Samuchaya Acharyas, when he explaining about the Loha Rasayana, he explained about the Ayush Pradata, Balavirya Karta, Rogapaharta, Madanasya Karta. न हि अयम समानम किंचित अन्य रसायनम श्रेष्ठतमो हि जंतु तस्मात् सर्वम प्रयत्नेन शुद्धम लोहम च मारयेत. So he explains about the different properties of the loha, and also he explains in the bottom line about the considering the better qualities of loha. Loha in the sense all the metals and minerals. So we have to get it into the better quality. So even though there are multiple references about the loha mado parikshet tathonantaram aushadam, as we say in the roganidana, roga mado parikshet tathonantaram aushadam. In a similar way, as rasashastris or rasavedyas, we have to carefully examine the loha mado parikshet tathonantaram aushadam. Otherwise, if you the selection is wrong at the primary stage, then all the process what are the efforts we are doing for the shodhana, marana, jarana, so everything will be failed. So hence these mineralogical identification carries very significant role to identify the proper mineral at the beginning stage. So these are the two important objectives. Then again, Murtani lohani rasibhavanti nignanti ptani mahamayacha abhyasa yoga drudadeha siddhim. So the acharyas have already given hint how we can get Drudadeha Siddhim Abhyasa Yogat. Then that means we want to administer this Rasa Yogas or Rasa Basmas for a longer duration. So that indicates that we are preparing a body for completely a different Drida Sharira. Then we are administering these medicines for a longer duration, and we have to go for selection of the proper Rasadravyas. Otherwise, what will happen? All the preparations, all the efforts, whatever we are putting it at the later stage, that will become in the vain. So these are the two important aspects into Rasashastra related. In the same way, when you look into the modern science, in the morning when I am looking into the physiological classifications, so there are different humanly physiological functions in the body, so which requires an essential element in the body functioning. For example, for cellular formation, we need to have sodium, potassium, magnesium, and calcium. For the day-to-day energy, we need to have iron, zinc, calcium, and molybdenum. And for structural and hormonal balance, for example, for structural calcium, we need for the growth of the bone and teeth, and we need a hormonal balance for iodine. Then we need to have the iron is also a nutritive element. So in looking into the functional, physiological functional aspect also, these minerals and metals will also carry a significant role. So these are the three different points. And at the end, so there is a curiosity among ourselves or as a Rasavedya. What is the percentage of essential elements in various properties of the mineral or various varieties of the mineral? Because we have different varieties of Abrak also, we have different varieties of Gairik also, and each and every classification of Maharasa, Uparasa, Sadharan Rasa, they have explained different varieties. In some cases, 3 varieties, in some cases, 4 varieties, and one has to look into all the minerals. Sometimes the acharyas explain only Grahya and Agrahya, which is Taija one, which is Grahya one. And we have to look into what are the structural or what are the compositional changes in Grahya variety and Agrahya variety. That will give some insight to understand that particular mineral. And when they are explaining about this one is the Uttama variety, this one is the medium Madhyama variety, and this one is the Adhama variety, and which is the essential element in this particular mineral, and which is changing the ratio wise. Whether that particular mineral the percentage is changing, that makes this mineral as a Grahya or Uttama one or Madhyama one or Adhama one. So that type of insights, when you look into all the metals and minerals, we will get a different type of understanding about the minerals, how to decide about or how to look into the particular minerals. So with this brief introduction, what we can assume is that we need to understand or we need to identify the minerals very stringently, so that we need to have the basics of mineral identification. So coming to the basic question, what is mineral? Because as we are discussing about the mineral or any property or any substances, when you define or when we want to understand, we need to know about that particular metal. Then when we don't know about that particular mineral characterization, so then only we can identify, or then only we can understand that particular mineral. For example, if I want to understand some people, then first what I will do know is what is the nature of that particular person and how he'll behave with the other substances. That is how we can understand different materials. The same things can be applied to the mineral. So when we talk about the mineral, to name a mineral, it should possess some qualities. There is a proper definition of the mineral, and it need to possess some particular properties to be called as a mineral. The first thing is it should be inorganic. The all the minerals, 99% of the minerals, they are inorganic in nature. So that means precisely it should not have the carbon hydrogen bonding in that. So inorganic material is not originated from the living beings. That is the general definition. But in the bonding level, this doesn't possess carbon and hydrogen bonding. That should be inorganic one. So if all the inorganic things are minerals, then no, because it should have the crystalline property. For example, the petrols, they are inorganic one, or simple consider water. Water in liquid state, whether it is a mineral, no, because it should fulfill the next quality, that is crystallinity. All the minerals, that should be inorganic, then it should also possess the property of crystalline. There should be a crystallinity. That means it should have a proper atomic arrangement or proper chemical formula. Then only they can be called as the minerals. For example, the same water, when it is in liquid stage, it is not a mineral, but when it becomes ice, then it is called as the mineral. The ice is a mineral, but water is not a mineral because it forms the crystallinity. So if the things are inorganic, then crystalline. Can we call it as a mineral then? For example, we have the glass material. That is inorganic one. It is crystalline one. Can we call it as mineral? No, it should also possess the third quality. That is, it should be naturally formed, so that we can call it as the mineral. So when you look into these properties, then how will you define it? Any mineral is a naturally occurring homogeneous solid with definite chemical composition and highly ordered atomic arrangement, typically formed through inorganic process. This is the proper definition of the mineral. So among them, some of the important things, that is our coral, it will not falls under the category of mineral because it is originated from the living beings. Then again, the same way, the pearl is also not considered as the mineral, as it is also originated from the living things. So this is the brief definition of the mineral. Now the next question is how the minerals are formed. So this is also very important question, because when we want to understand a particular substance, we want to also know about its origin, how they will be formed. Usually the 90% or more 100%, we can say the minerals are formed from the eruption of the magma from the earth crust, and the molten magma which is coming out of the earth crust layers. It will sediment in and deposit into different, it will come along with different elements, and it will deposit and forms various elements. So most of the minerals that make up the rocks and the crust and mantle formed through the cooling and freezing of the melted magma. So the magma will come out on the surface, and it will be cooled down with a rapid cooling or slow cooling. If it cools rapidly, it will from the grains of the crystals. Grains are nothing but the crystals which are having the size of less than 1 mm. They are called as the grains. And the rapid cooling makes it to form the grains. And if the magma cools slowly, then it will form the large crystal varieties. And along with that, there are other methods how the crystals will be formed. The second is when the cooling is rapid, that I have explained. The crystal form at once, and only small mineral grains will form before the rocks become solid. Because the rock to become solid, it will take more time, but the small grains will precipitate very easily, and they will form grains. Then, when this is also I explained, when cooling is slow or when few crystals are growing at a time, relatively large crystals will develop. So the cooling process, if takes time, the large crystals will develop, and if cooling process is very rapid, then the small crystals will form. And apart from that, there are other two procedures how the crystals will be formed. That is by the precipitation of the solutions. If magma comes and falls into the different water bodies, then the water bodies will absorb the different minerals or water soluble minerals. Then that will lead to the precipitations. When the water evaporates, that will lead into the precipitation. Look into this picture. This is the lake. Then when it is the water portion is reduced in the lake, there is the formation of the crystal structure. This is a calcite. The calcite, initially it is absorbed in the water. It is a solvent. When the lake goes on decreasing its water level because of the heat and water evaporation, the calcite crystal will be formed in the lake's edges or lake's surface. So this is how the precipitation crystals will form. And this is one more method of formation, that is precipitation from the gases. Usually in the volcanic eruptions, there will be different gases will come out from the volcanoes. Here it is an example, typical example for the sulfur fumes. The sulfur fumes are depositing in the different layers of the earth, and they are sedimenting, and the crystals are forming. The sulfur will come in the gas also, and some you can see in the picture also in the right side, there will be liquid sulfur also, that is sedimenting, and it's forming the different rocks of the minerals. So these are the two other varieties of formation of the minerals. And apart from that, there is one more phenomena that is called as metamorphism. So when the crystals or when the substances are undergo the different type of or the higher temperature and higher pressure, they will transform their nature. The solid minerals react with each other under high pressure and temperature, and new minerals are formed. So this is the case of, for example, in case of diamond, even the graphite, when we put a graphite into higher pressure and high temperature, then the same graphite is converted into diamond. That is called as metamorphism. So this is also one of the method or the type of formation of the crystals or the minerals. Then we have weathering. So once the volcanic eruption happens and different metals or minerals are deposited on the surface of the Earth's crust, then these metals or minerals, they will not keep silently. That means they will react with their neighboring materials, whether it is oxygen, whether it is a water, or whether it is any acid, and with reacting to other materials or other substances, they will change their nature. The metals will form metal oxides, and then sulfates and carbonates. Likewise, there are different types of minerals will be formed. That is how we are classifying the different types of minerals in next slides. So the weathering is also one of the important criteria to in the formation of the different types of minerals. So this is the brief introduction how the minerals are formed. One is from the magma, the second is from the precipitation of the solvents, and then the other one is from the precipitation of the gases, and third one is from the metamorphism, and other thing is the metamorphism. So the metamorphism is very rarely seen, but in weathering is important for us, because most of the our minerals are formed because of the weathering. So this is how the minerals are formed. So this is one of the picture which is indicating again the sulfur fumes, huge sulfur fumes. There are and it is the sulfur fumes are moving, and wherever these sulfur fumes are go on deposit on different minerals, the sulfides will be formed. So that is how the surface metals or surface minerals will react with the neighboring metals or minerals or neighboring structures. Now into the various forms of minerals, the classification of the minerals, mainly based on the composition. The minerals are classified into 8 to 10 groups. So I have selected the classification which is relevant for our Rasadravyas, and which are not much relevant for us, I have not tried to include in this section. So these are the different types. One is sulfides, which is mainly having sulfur group. Then sulfate group, SO4 group, the one sulfur and four oxygen groups. The second group is sulfate. And then carbonate group, CO3. We can see so many Rasadravyas which are having up the carbonate groups. Then phosphates. Phosphate is also one of the important group for us also, and for the purpose of the fertilizers. In the phosphate is frequently used as a fertilizing materials. So this is also a mineral of interest for us people. Then for the farmers also. Then we have silicates, which contains a silica tetrahedron as the basic unit. Then we have halides, the halides materials, which are the halogen group of metals from the periodic table. Then we have oxides, different metals reacting with the oxygen group and forming oxides. Then we have native elements. So these are the different varieties of the or classification of the minerals based on their chemical structure. We have classified for our understanding these minerals. Now we look into each and every mineral group one by one. So that we can understand little basics of the these groups, so that will indirectly help us to understand how to identify the mineral. The first one is the silicate minerals. Though silicate minerals are very common in earth crust, about 90% of the earth crust is contained of silicate minerals. Some are useful for us, some are not useful for us, some are rock forming minerals. They are the granite and all, they all come under the silicate group of varieties because they are rock forming minerals. The silicate which contains silicon groups, as we see in the right side diagrammatic represent, there is one silica group and which is bonded with the four oxygen groups. That is called as silica tetrahedron. This is the basic unit. Because this diagram or this picture is very, very important, because again silicate minerals are classified into different further sub classification, sub groups based on their nature to bond with the oxygen. If this silica tetrahedron basic unit, it keeps on repeating SiO4 multiple times, then that group will different. When one silica tetrahedron group combines with the another tetrahedron group and shares the one oxygen group, then it will become SiO7. Yes, sorry, Si2O7. Then that will become another group. So thus, that to understand that basic nature, so we need to understand this silica. Is my cursor is visible?
Yes.
Yes. Okay. This is the silica and these are the four oxygen groups. This is the basic unit. Just we need to remember this. This is the basic structure of the silica tetrahedron, so that we can understand the next upcoming slides. So basic building block, as we can say, all the silicate minerals are formed with this silica tetrahedron, SiO4. And this silica tetrahedron can combine in different ways to form various metals and various silicate minerals. So that we have already explained. And examples are the quartz, feldspar, mica, amphibola, pyroxene. These are the different examples. And the students, you can keep it in mind that the maximum examples I have tried to incorporate here are from the Rasadravyas. Wherever there is not possibility of taking any examples, we have taken some other examples, but I have tried to include maximum examples which are of our Rasadravas. The name is in scientific nomenclature. We have not used any Sanskrit terminology, but you can easily guess which drug is which one, because since UG time we have known what are the Sanskrit names for each and every mineral. So the quartz we know, the Uparatna Spatikam. Then feldspar we know again it is Uparatna, Suryakantamani, sunstone. Then mica we have no Abraka and everything. So all the examples are tried to use Rasadravyas here. So this is about general introduction about the silicate minerals. Now come to the first variety of the silicate minerals, that is neosilicates. So neosilicates are the silicates where there is, as I explained earlier, the basic unit is repeated here. That means the SiO4 is go on repeating in the formation of the mineral. When you look into this is the same picture what I shown in the earlier, that is silica with the four oxygen compounds, then which is repeating in each time to form the mineral. None of the oxygen atoms is shared by the other tetrahedron. The one same, the tetrahedron silicon is placed with the another. There is no sharing between the oxygen groups. This forms the neosilicate groups. And the chemical formula usually contains the multiples of SiO4. For example, SiO4 twice, SiO4 thrice, there is no change in the SiO4 or silica tetrahedron group. And some of the best examples for this are zircon. Zircon SiO4, we know zircon, which drug we can call it as zircon. There is a little bit of difference of opinion among the concentration of zircon as a drug for Gomeda. Within Ayurvedic Pharmacopoeia of India, for Gomeda, they have considered it as the almandine, not zircon. So that difference we can show it to you in the next slide. But usually in the previous textbook, the Gomeda is given the name of zircon. They compared with the zircon. But zirconium is the essential element in the zircon, and iron and aluminum are the essential elements in the almandine. Then topaz, we have topaz, aluminum silicate. That's also a common drug for us. Then we have peridot. Peridot, the students can note down, and in the discussion, I will ask what is this drug, so that they can tell what is the peridot and what is the Sanskrit name for that peridot or topaz or almandine. So when you look into this picture, zircon, topaz, and almandine, these are the comes under the neosilicates. So this is the zircon. The mainly color of this particular zircon is mainly presence of the zirconium element. Then look into this is the topaz. Then we have almandine. So when you compare zircon and almandine, they are looking almost similar. Just there is a little bit change in the color. This color is mainly due to the presence of zirconium in the zircon, and this is mainly due to the presence of iron in the almandine. And most probably due to the presence of iron, this almandine is considered as the drug for the Gomeda. I don't exactly what is the reason, but I feel because of the presence of iron, which is an essential element for the bodily functions, that's how they may be concluded the Gomeda as the almandine. In the AFI, the Gomeda is correlated to the almandine. So these are the some of the examples for the neosilicates. Then second group of silicate, that is sorosilicates. Here the same structure, silicon tetrahedron, then which will share one of the oxygen molecule to the next repetition of the silicon tetrahedron. For example, here when you look into this diagram, these are the two silica tetrahedron groups, but one oxygen is shared in between the two silica tetrahedron groups. Hence, these are called as sorosilicates. Hence, the formula is Si2O1, Si2O7, because there are two silica materials and one, usually they need to have 4 oxygen groups. That becomes 8. But here, when they shared one oxygen common, that will become Si2O7. So hemimorphite is one of the best example for the sorosilicate. That is calamine. Hemimorphite is nothing but the calamine. This is calamine, one of the best ore, or one of the ore for zinc. When you look into the different ores for the zinc, the calamine is one among them. So that is a hemimorphite. Then this comes under the group of sorosilicates. So this is the picture of hemimorphite, or we can call it as the calamine. Next, the third group, we are having cyclosilicates. The same thing, the silicon tetrahedron is sharing it will forming a ring-like structure. When you link it to these two diagrams, there will be formation of ring-like structure. So that will form the cyclosilicate. Hence, the name is called as cyclosilicate. They are forming a cycle. Then each tetrahedron shares 2 of its oxygen atoms with the other tetrahedron. When you look into the oxygen groups here, this tetrahedron is sharing this oxygen and this oxygen as a common for the neighboring tetrahedron group. And this tetrahedron sharing these two, and this tetrahedron sharing these two. Hence, the second variety, they are sharing only one oxygen atom, but in the second variety, or we can call it in the cyclosilicates variety, they are sharing 2 oxygen atoms in common. And one of the best examples is tourmaline. The tourmaline is one of the best examples for cyclosilicates. And in the same way, when you look into the external structure also, the tourmaline usually comes under the cylindrical form. So when you look into the picture of the tourmaline, why it is in cylindrical form? Because the internal structure of that tourmaline is made from the silicate variety, that is cyclosilicate. So when we understand, then we'll come to know that the cylindrical nature of that particular tourmaline is because of the internal structure, internal chemical bonding, which is sharing the two oxygen atoms and the forming the cyclosilicates. So that will give us idea to understand. And it is not always true that the only the internal arrangement of the atoms will help in forming the external appearance or external crystal habit. The other factors are also influencing, but this is also one of the important criteria, or one of the important base how the crystal habit is formed. So the cyclosilicates have chemical formula SiO3. All the cyclosilicates which will form SiO3 here, because the silicon 1, or you can call it as X, and oxygen 3 into X. That is the basic formula. When we multiply it with the 3 into 3, it will become the Si3O9. If the silica are 6, then it will become 6 into 3. That means 18. The chemical basic nature is SiX, then O3X. That is the basic nature or basic chemical formula of the cyclosilicates. So this is the tourmaline. There are various varieties of the tourmaline, and when you look into these different pictures, even though they are formed in different way, but when you look into all the pictures, there is one thing is evident, that they are forming a cylinder-like structure. You can see all the cylinders-like structure. This is how the tourmaline is formed. This comes under the cyclosilicate variety. Now we'll move into the next variety, that is tectosilicates. So what happens in the tectosilicates is, the tectosilicates members group compounds with structure that have silicate tetrahedron arranged in a 3-dimensional lattice. Here first they have 1 oxygen atoms are shared, then they have shared 2 atoms, then they formed a ring, then here they have formed a 3-dimensional lattice. When you look into this diagram or this picture, you will understand how the silicates are arranged in a 3-dimensional way. Then they are sharing then each of the 4 oxygen atoms of a given tetrahedron is shared with the another tetrahedron. That means all the oxygen atoms are sharing with the other oxygen atoms. All 4 oxygen atoms are sharing to the other oxygen. Here there is connectivity to 1, 2, 3 and 4. There are 4 attachment to the each oxygen elements, and they are forming the tectosilicates. And these tectosilicates are very, very important because the most of the chords comes under the tectosilicate groups. Even our feldspar, that also comes under the feldspar group, also comes under the tectosilicate group. Because of the there is a nature in the combination of the different elements. Again, the feldspar group will form different varieties that we will see in the next slide. But just we want to keep it in mind that the tectosilicates are formed by sharing the 4 oxygen groups in each element, and it will form the 3-dimensional lattice. So when you look into this diagram, the feldspar triangle, this triangle, the feldspar is formed in a 3-way, because it is also formed by the rich potassium aluminum silicate. Then here in the left hand corner there is sodium aluminum silicate, and here in the right hand corner calcium aluminum silicate. So based on the combination of the elements present, it will form into different types. The microcline and orthoclase, they are more of potassium rich feldspars. Then we have sodium aluminum silicate, that will form the albite. Then we have anorthite, they are calcium aluminum silicates. These silica groups, based on the neighboring element, presence of the neighboring element, they will combine with the different materials, either with the potassium, either with the sodium, either with the calcium, and they will form the different materials. So, and again, one more example for our this silicate group is carnelian. Carnelian is mainly, we call it as Rudira, one of the Uparatna Vargiya Dravyas. We call it as carnelian. So this is also one of the important drug for us, and this also comes under this silicate group. Then we have Puttika. This is peridot. We can call it as chemically, we can call it as peridot. That is called as Puttika. This also comes under the Uparatna Vargyas. Then this drug is also comes under this silicate variety of the groups. Then mainly the chords The quartz picture I have not included here because again in the next slides, the quartz will repeat in many times because quartz becomes the most significant example for different crystal habits and other things. So I have not shown the picture of the quartz here, but the feldspar, that is also one of the important drug, that is Suryakantamani. Some authors, the textbook have called the correlated the feldspar to the Suryakantamani. Then this carnelian, that is Rudira. Then this is Puttika, that is peridot. Next, the variety is phyllosilicates. So in the same variety, we have the silica tetrahedron. Then in phyllosilicate structure, the tetrahedrons are arranged in the sheets, layers. So this is the typical structure of the phyllosilicates. They are arranged in a sheet, and these two silicon groups, they will form the interconnected with a 6-membered ring of silica tetrahedron. So these two tetrahedron groups or silica tetrahedron groups, they will interlink with the other 6 tetrahedron groups so that they will form the sheets. Can we when we count this, these are the 6 tetrahedron groups. Here also there are 6 tetrahedron groups. Among them, these are the common 2 tetrahedron groups so that they will form the different layers. So the one of the best example for is how the silica is removed by layer, our mica. You know mica abraka, the patrabraka. Why the patrabraka form the sheet rather than a lump or rather than a cylindrical structure? Because the basic nature or basic chemical composition of the abraka is based due to the formation of the phyllosilicates. Here the silica tetrahedron is arranged in a layer wise. So 6 silica tetrahedrons are shared with the 2 common tetrahedrons and forming the layer-like structures. So examples are talc and silica, our Dugdha Pashana. Dugdha Pashana is also a layer, but as it is having a very soft in nature, and hardness is only 1. So the layers are not visible. When we try to remove it with the layer, it will break down. So that's why we are not able to remove the Dugdha Pashana in a layer by layer. But when you look into the Dugdha Pashana mineral as observed, and then you can see the small layer-like structures inside it in the external observation. But in Patrabraka, easily we can differentiate the formation of the layers. So this is the Dugdha Pashana, and you can see layers on the top of the surface of this Dugdha Pashana. The talk here, there is a presence of layers, but we are not able to remove it because the stability is not there in that layer because of the soft nature of the Dugdha Pashana. But in Abraka, we will see. But Abraka picture I have not shown here because we will see the Abraka pictures in the next slides. Next, this completes the silicate groups, that is silica tetrahedron groups. We have started with the first one is the silicate groups. Again, there are various classifications when you get to subclassification of the silicates. So hence the first group of minerals will be completed. Now we are going to the second group, that is sulfides. As we know, the sulfide mineral is the group of compounds which forms with the sulfur with 1 or more metals. When the metal elements or single metal or combined metal forms a bond with the sulfur, then it will form a sulfides. And usually 2 valencies are there for the sulfur to combine with. Then most of the sulfides are exhibit high symmetry in the crystal form and have many of the properties of the metals. When you look into the different sulfides, they look like metals. Sometimes it is very difficult to differentiate just by looking into sulfides as the sulfides. They look like metals. We will illustrate with the examples and including the metallic luster. Apart from the metals, the sulfide groups having the metallic luster. That is one of the important point one has to remember here. And often they are strikingly colored and have low hardness and high specific gravity. These sulfides will have the very vigilant color. The color is very definitively marked. Then we can differentiate exact color. Then the hardness is little bit low compared to the metals, but specific gravity is high. That is all the different qualities of this sulfides. And examples, here we have pyrite, you know which is the pyrite. Then we have lead sulfide, galena. Then we have sphalerite, one of the important ore for zinc sulfide. There are different variety of sulfide groups, and most of our drugs, Rasadravyas, falls under these sulfide groups. So look into these pictures. Here we have different drugs. We have galena, lead sulfide. We know This is also one of the drug for interest. And this is chalcopyrite, which is containing two elements and with sulfur, copper and iron. Tamra ayasa gandhajam. Tamra is there, ayasa is there, gandha is there, sulfur is there. Then we have zinc sulfide, and one of the important ore for zinc. Then we have molybdenite, which is also an important essential element. Then we have pyrite, Vimala, we can call it as Vimala. We compare the pyrite to the Vimala, FeS2. Then we have bornite. The bornite and chalcopyrite are having the same chemical units, but there is change in the ratio. Here CuFeS4, but in the chalcopyrite there is CuFeS2. And sometimes this bornite is also called as peacock's ore. When you look into the copper ores, when you are studying about the different copper ores, this bornite is considered as the peacock's ore. So this is also one of the important ore for the copper. Then we have arsenopyrite, one of the important source for arsenic and iron. Then we have stibnite. Stibnite is also important because this is our anjana. So srothanjana compared to the stibnite, and which is available in the form of sulfide. So these are almost all the sulfide mineral are of interest for us. So knowing the hardness, knowing the luster, knowing the streak of all these sulfide minerals is very, very important when we are going to discuss about the properties of the minerals. These properties of the minerals should be kept in mind so that we can identify, because without knowing the properties of each and every mineral, directly we jump on to the assessing the properties, then it is very difficult to understand. So that I have tried to incorporate simple basics of these groups of minerals. Next, we have sulfates. This is the sulfide groups. Then we have sulfate groups. These sulfate groups are naturally occurring salts of sulfuric acid. Usually, they will contain the SO4 group. The sulfuric acid will form different salts with reacting the different different elements. Then it will form the sulfates. And there are two types of sulfates: anhydrous sulfates and hydrous sulfates. So when the sulfate along with the metal, when it react with the it forms bonding with the hydrogen, then it forms the hydrous sulfates. And when without the hydrous, it will form the sulfate group. For example, CaSO4, there is no hydrous group in that, that is anhydrous group. CaSO4 2H2O, that is hydrous group. CaSO4 is there, along with 2H2O is there, that is our gypsum, Godanti, that is comes under the hydrous group. So all the hydrous varieties of sulfates are our interest, because our 3-4 drugs of Rasadravyas will come under this hydrous sulfates. For example, first one is the gypsum, because it is CaSO4 containing 2H2O, two water molecules. Hence, it comes under the hydrous variety of sulfates. Can you name another some examples where there is a water molecule and which falls under the sulfate groups? Just if you think some of the most common drugs, that is chalcanthite. Chalcanthite, that is CuSO4 5H2O. One of the ore for copper, Sasyaka, we can call it as Sasyaka. That is CuSO4 5H2O. Then we have, this is the picture of the chalcanthite. Then you can see the blue color in the mineral here at the inside of the mineral. This chalcanthite is usually formed nearby the copper ores. When copper is exposed to the weathering, initially we have discussed some of the points in the formation of the minerals. The weathering is one of the important criteria in the formation. When the copper material is exposed to the weathering, it will react with the oxygen, water, then it will usually form the chalcanthite. That is the copper sulfate with hydrous copper sulfate in water molecules. This is the formation of the chalcanthite. Then we have one more important drug, melanterite, FeSO4 7H2O. That is one of the important drug of our interest. Can you name? Anybody can name this drug? Yes, madam. So here there is the 7 water molecules. We can see there is the formation of melanterite here in the picture. Usually it is formed nearby the iron ores. Khasisa and Tutta, green nutriol and bluetriol. We used to remember these drugs by the most common names like green vitriol and blue vitriol. They are nothing but the chalcanthite and belanthite, which comes under the sulfate groups. That is under that the hydrosulfate groups. So gypsum, chalcanthite, and belanthite. These are the three important drugs which comes under the sulfate groups, hydrous sulfate groups. And even the potassium, I have forgot to explain. The potassium is also comes under the sulfate group, having the 12 molecules of water. Potassium aluminum silicate or potassium normal alum, that is also comes under this sulfate variety. It also contain SO4. So these are the these all are these drugs are interest because they comes under the our Rasadravya classifications. So that is the picture of the potassium at the end. Now this is the sulfate minerals. Other pictures here, as I told, anhydrite CaSO4. There is no water molecule. In the same anhydrite, when it forms a bond with the water molecule, then it forms the gypsum. And then barite and celestite are other examples, but these are of not our interest. So we'll move ahead. So this completes the sulfate minerals. Next we have halides. So the next classification of the minerals will halides. The halides are the different groups usually formed from the these are the salts of the halogen acids, and these halogen materials or halides are the group of halogen group from the periodic table. Group 7 in the periodic table contains different elements: chlorine, fluorine, bromine, iodine. So when different elements react with these halogen groups and forms the mineral, they are called as the halides. So these halogen elements, mainly the fluorine, chlorine, bromine, and iodine, then they react to form different types of the halides. The examples are our calamol, one of the important ore for our mercury, Hg2Cl2. Here the chlorine is the halogen element, and it combines with the mercury, it will form the calamol. Then we have salmoniac. Salmoniac is our Navasadra, ammonium chloride. This is called as salmoniac, ammonium chloride, and the ammonia reacts or binds with the chlorine. It forms the salmoniac, NH4Cl. Then fluorite. When the calcium binds with the fluorine, then it will form the fluorite. So these are some of the examples for the halide group of minerals. So these are the pictures of the halide group. The important halide mineral, what I have not explained, is the halite, because halite is the most commonly used mineral, not only in the medicine, because in day-to-day our food also, that is salt, common salt, sodium chloride. So this is also comes under the halide mineral. So what is the important thing what you have to notice in the halite is that just look into the picture how the crystallization has been formed. This is the cubic in nature, and we have the crystal part is growing more. The inner crystal part is not growing. The outer crystal part is growing. This picture is just you have to keep in your mind. We will discuss about this in the crystal habit, but this picture you have to keep in mind. And these are the different other halide minerals. So this completes the little bit basic introduction about the halides. Next we have oxides. The oxides are very important because most of our Rasadravyas falls under these oxides. And as you all know, these are again naturally occurring inorganic compounds with structure based on close packed oxygen atoms, in which smaller positively charged metals or other ions occur in the interstices of the oxygens. If different metals go and bind or sit into the interstices of the oxygen bonding, then it will form the different oxides. Here look into this picture where this is an Al2O3, one of the important mineral, Al2O3. There are oxygen atoms, then this aluminum goes and binds in between the oxygen bondings. So that will form the oxides. It contains one or two metals. The usually oxides will be formed by either single elements, or it may be formed by the two metals. Then oxides are distinguished from the other oxygen-bearing compounds. Even though we have carbonates, silicates also having the oxygen group. Carbonates will have also oxygen group. Then borate will also have the oxygen group. But these oxides are differentiated because in all the other cases, for example, in carbonates, the carbon is the center element. Along with that, the oxygen bonding is happened mainly to the carbon, not to the element. Hence, these groups are not comes under the oxygen. Same way with the silicate. In silica, as you say, silica tetrahedron. Silica is the internal, the main structure. The silica is bonded to the oxygen material, not the element. So hence they are not considered under the oxides. The carbonates, borates or silicates, they are different groups because of the bonding of the oxygen to the particular element. So here this oxygen is directly bonded to the metals. The main core structure of the carbonates and silicates are different. That's why the oxides are different and these silicates and carbonates are different, that we have to keep in our mind. So these are some of the oxide minerals that is very, very important for us because these different drugs are very much of use in our Rasashastra. For example, hematite, one of the ore for iron. Then we have magnetite, that is one of the important ore for iron. Then we have corundum. Can anybody name what is corundum is? Corundum comes in Ratnavarga Dravyas. Or Manikya. Manikya is sub-classification. Ruby is sub-classification corundum. Ruby and sapphire. Ruby and sapphire are the varieties of corundum. So this is the corundum, that is ruby. Red ruby, you can see the last picture here. This is the ruby, red ruby. But the corundum is formed in different colors also. There is not only the red corundum, but ruby is famous because of its the gem nature, the clarity, cut, the carrot, and all these things. When you discuss about the gemology, all other things also comes in picture. So now we will not discuss about those particular terminologies here. We only concentrate on the minerals. Then this one is the sapphire, neelam. This also comes under the oxide mineral. This is the sapphire, neelam. So these are the different oxide minerals. The corundum and the sapphire are very, very important. Ruby and sapphire are very, very important because this comes under the corundum group, and other minerals are also very much of interest. Now, in the same category, now we have oxide groups, chrysoberyl. So recently, I have, there's a small, 2 minutes I will take to share the small story. Recently, I have went to a movie recently in Karnataka and all over India. There is one movie which is very famous, which gains popularity. That is Kantara movie. So, and in that movie, there is a one scene. How many of you have seen the Kantara movie? Just raise your hand. Only few. Okay. And fortunately or unfortunately, I have went to movie along with my wife and daughter. So this is the most difficult thing to carry family to the movie, because daughter will not leave us to, because she is just 4.5 years old, and for each and every scene she has the question. So he will, the mom will leave the daughter in my lap, and she has go on asking the questions. So when this scene comes in the movie, there is a typical scene in the movie that when tiger comes very closer to the actor, the main character of the film, his name is, I think, Burme in the movie. So the reflection of that tiger's eye is also illuminated in that character, or that the lead role person, Burmese eye. That is called as Chatayansi. Our Vaidurya is having that Chatayansi property. So cat's eye, we usually call it as cat's eye. So I need to explain my daughter about, because this scene is very, very interesting scene in that movie, and I have lost interest in explaining to my daughter, because this is an important scene. I am not able to skip that scene also, and I am trying to explain to my daughter also. That's how we are discussing Rasashastra in even theaters also. So this is an important sign in Chatasi property, which is mainly we see this different materials, Vaidurya. There are different phenomena. This Chatayan property or Chatayansi property is mainly the reflection of the fibers, silk-like small threads fibers present in that particular group of the minerals. Though what will happen, that will reflect the light into the silks, and they will reflect the light, and they will formation of thread-like appearance in the thread-like appearance of the mineral. But in tiger side, it is little bit different. That is mainly because of the less absorption of the light molecules from the retina. The tiger's retina will not absorb all the 100% light in the whatever the thrown into the retina. It will reflect some of the light, so that when in the dark, when you put a light onto the tiger's eye, the eyes will be reflecting. So that is how it will use. They'll say that the tigers having the visibility of around 6 meters in the night, which is much larger than the human beings. So that is the property, Chatayansi property. They are correlated, and we usually remember it as a cat's eye. That is a typical property called as Chatayansi, and that visuality is deflected very nicely in the that Kantara movie. So those who have seen, it's nice. Those who have not seen, I recommended them to watch for this Chatayansi property. So next, this is about the next group, that is native elements. So after the oxides, then the last group which is left is the native elements. There is much to say about the native elements, because all we know, the native element, there is a single element present in its original form. For example, gold, silver, and sulfur. They all are available in the native form also. But usually you are not able to find native elements, because one or the other metal, usually they will come in contact with the other metals or weathering other things like oxygen or hydrous, and they will take into different forms. As we discussed earlier, either carbonate or sulfate or different materials. Whether I'm going slow, sir, I need to accelerate.
No, sir, no, sir.
Okay, thank you, sir. Because I thought this is a basic introduction is very, very important to understand. So I kept these things. I will accelerate a little bit. So this is a Saturday afternoon, maybe half day for you all. I don't know.
No, sir. Good.
Okay, sir. Okay. Then best examples are the gold, silver, copper, and sulfur, and diamond. These are available in the native form. So this is how native elements will be available. And this typical nature of the crystal formation, gold, you just need to observe, because this habit will come under the crystal habit, the arborescent variety, the tree-like growth appearance that will usually seen in the native elements for silver and gold or copper. So dendritic and the arborescent variety, these are the very important. Dendritic is the crystal habit, and arborescent the fracture. So these are the two things just we to keep in mind when you are discussing the properties. These things will come. And this is sulfur. Just by look also we will identify, because sulfur we will show so much time, so there is no much confusion. So I think another group hasn't left. I thought all the groups are covered. Carbonates. The one more group is the carbonates. And then, as we know, we had discussed the basic structure of this carbonates is CO3. Then this CO3, the carbon is bonded with the 3 oxygen molecules and it form the different materials. And the carbonates are among the most widely distributed minerals in the Earth's crust. And this is also very, very important because of the calcite or dolomite and azurite. They are all of the carbonate variety. So these are some of the examples for the carbonate variety. For example, calcite is COCO3. The lower portion is the calcite. Then siderite is one of the important ore for iron. And this is also one of the cause for the one of the lung disease that is called as siderosis. The workers working in the iron mining, they inhale the dust of this material, iron material, siderite, then form the disease called as siderisis. Then azurite is one of the important copper ore, thus comes under the carbonate mineral. Then we have magnesite, which is again combination of magnesium and carbonate. Then we have malachite. This malachite is also very, very important because of this also one of the important ore of the copper. So these are the carbonate minerals. Then we have one more group, phosphates. That is the PO4 is the main basic element in the phosphate, where the 4 oxygen elements are bonded to the phosphor. So the phosphates can be divided into the primary phosphates. That means they are directly crystallized in the liquid from the magma. Then secondary phosphates, there is alteration of primary phosphate due to the different phenomena. And third one is the fine-grained rock phosphates formed at the low temperature from phosphorus-bearing organic materials, primarily underwater. So these are the 3 varieties based on their formation. They have classified into different varieties: primary, secondary, and fine-grained varieties. So among them, turquoise is our interest. That's why we need to study about the phosphate. Can anybody name what is turquoise is? Pyrojaka is a turquoise drug. Hence, this phosphate group is very, very important for us. Again, which contains copper, aluminum phosphate group, and it is also a hydrous variety, which contains the water molecule also. So these are the phosphate groups. So I think this ends the introduction about the basics about the different classes of the minerals, so that we can have just a little bit information about the all the different minerals. And what I will request for all the students is that just you can classify all the minerals and note down the different properties of the minerals. For example, silicates. What is the hardness of these silicates? How will be the streak of these silicate groups? How will be the crystal habit of these silicates? Like that, each and every group, if you have an idea in your mind about this group and what are the important parameters, then what we are discussing now onwards, that will be very, very useful. Again, I have not tried to cover all those things because it is again a lot of time consuming. So I just kept the basic information things, so that once we know all the physiology, so all the mineralogical properties of all the minerals.
Excuse me, sir.
Yes, yes, sir.
Sir, if possible, we can do the second part also next month, like this.
Definitely, sir. I am very interested to do the second part also. There is no issues. There is no issues, sir. Just we finish these lectures, and just we can take the feedback of the students whether they are interested in this or not, or whether I am able to convenience them, or I am able to cater whatever their needs are, like that. And if they are interested, we can go ahead, sir. No issues. So now this I can consider it as a second part of this same session. So here now onwards, this is very, very important for the identification of the minerals. So whatever we have till now understood is the different properties of the minerals, how they are formed, what are they, and what are the some of the important properties of the minerals. And once we are known about these things, now we need to use all those properties to identify the mineral, because we know how the Kohli bats. Then if it's a typical without showing the Kohli's face, then just if they show the cover drive of the Kohli, then we can identify that this is Kohli's cover drive, because we know the property, because we understand Kohli very much. We have seen that phenomena repeatedly. That is fixed in our mind. So in the same way, when you repeatedly look into the mineral groups, when you identify the different properties of the minerals, then easily we can identify, and we can use those phenomena to identify the minerals. So how we can identify the different minerals? By observation with the color, or with streak, with luster, or with cleavage and fracture. That is, cleavage and fracture are the how the mineral reacts when it is applied to the pressure. Then the hardness, how hard it is. And other two things are specific gravity and instrumental techniques. And usually today's class we will cover only the non-instrumental techniques up to the hardness, and we will leave it to the specific gravity and instrumental techniques not covered in this particular lecture. So these are the same things: color, luster, texture, and streak, hardness, cleavage, fracture. So the first one property of the mineral is the color. How important color is? The color is always important, because the first impression is the color. When you look into some of the minerals, we will identify just by color, looking into the color. But is that a good sign to identify a mineral with the color? Usually not, because even though color is the most obvious property of the mineral, because each and every mineral should possess one or the other color. The color should be there. It is not like that the color is absent. The color should be there, but it is often non-diagnostic. Why? Because the same mineral will be having different colors, and the different minerals are having the same color. So that's how it is. The color is very, very difficult. Based on the color, we can't identify the minerals. So the mineral is one of the property we can help in identifying, but it will not give the 100% idea about the particular nature of the minerals. Hence, the color is the obvious property, not a diagnostic property. As I explained, a single mineral have wide range of colors. I will show it into the example. Then the colors are color variations. Why there is a variation in the color of different minerals? Mainly because of the presence of the trace elements. Because these all minerals are formed in the earth crust, and we don't know which element is sitting behind or sitting beside that particular mineral formation. Now, whatever mineral will engulfed in the formation of the crystal, it will exhibit its color. If iron, there will be color. If it's other element, copper, there will be different color. Whatever the element will be there, along with that, the mineral will be, the color will be different. Even some of the crystal defects, for example, the fracture of the color mineral also gives into different colors. So as you all know, this is one of the typical example of the one of the mineral. What is this? Look into the second picture. What is this? And look into the Third picture. So these are all varieties of quartz. Because of the presence of the trace elements, they are looking different color. So hence the color is not an obvious property. I will show it in more clearly in the next diagram. So look into these different pictures. There are different varieties of quartz. Initially, I have told the quartz diagram I have not showing in the silicate variety because I have used this diagram here. So anyhow, I am showing this quartz in multiple time. So this is the colorless quartz. Then this is the milky quartz. Then we have smoky quartz. Then the amethyst, that is also variety of quartz. Then citrine variety. Then rose variety. And what is the cause for the change in color? The milky quartz gets its white color from millions of tiny fluid filled cavities. So here what you are seeing is the milky quartz. It is reflecting the light because inside this milky quartz there are small tiny fluid filled cavities in the formation of the crystals. Hence the light is not passing completely as like the colorless quartz. So colorless quartz is vitreous in nature. It's a water-like appearance. But the milky quartz, even though luster is vitreous, but it's not exactly the light rays are passing because it is reflecting the light with the presence of small fluid-filled cavities. Next is the smoky quartz. Smoky quartz gets its gray color from the structural damage caused by the natural radiations. So smoky quartz, if there is a structural damage, hence the vitreous luster will be lost and it will look like a smoke-like appearance, dull appearance. That is because of the structural damage. Then we have amethyst. This one is the amethyst and citrine. They are mainly because of the presence of iron in them. The trace element is the iron, and they will look into different colors, the amethyst and the citron varieties. Then we have rose quartz. That is because of the manganese. When the quartz formation, it have the trace element manganese, it will look like rose quartz. So the Uparatna Spatikam is all our quartz. Then which Uparatna Spatikam, which variety you have to take, then you have to decide because in the introduction, I have put forth the one discussion point that is based on the percentage of the trace element, which is helpful for us, which is not helpful for us. And which variety we will get, whether the manganese is helpful for us, whether iron is helpful for us, that we have to decide so that we can discuss on that. That is the discussion points for us when we are identifying the Grahya or Grahya variety. So this is how the quartz are different color. That is, color is important for identification of the minerals. The second point is the luster. Now, what is the luster? The luster is nothing but the overall sheen of the surface. How the light reflects on the surface of the mineral. The color is the obvious property, which the overall color, but the one just on the surface, how the light is reflecting on that. That gives a different lusters. So then this is distinguished easily by the human eye if the material is having different lusters and with some practice. But this is not quantifiable because we can't measure the luster with definite parameters. There is a 5 luster, there is a 10 luster, nothing like there is no measurement in it because it is depending upon our eyes. We are assessing the luster. So this is how the light is reflecting on the surface. And usually the materials which are opaque, they will give different types of lusters. And usually the metals will not give any metallic luster. Apart from metallic luster, they will not give any luster because they are not passing any light. Now I will show you with more conveniently with the next examples. So usually the luster is divided into two groups. That is, one is metallic luster and another one is the non-metallic luster. The metallic luster, that is an obvious property of metals which will shine, or you know the metals. And even with the sulfate groups, when you are discussing the copper sulfate and all, I have told that this sulfate group also possesses the metallic luster, the copper pyrite and all, then iron pyrite, copper pyrite, the metals and the sulfates. These two groups will have the metallic luster. And apart from that, there is a non-metallic luster. Again in the non-metallic luster, there is again different varieties. There is vitreous variety as there in the quartz. There is earthy variety as there in the Gairika. There is silky variety as there in the asbestos. There is a resinous variety, resin-like appearance. Then there is a pearly variety even in mica. There will be shine, will be pearl-like appearance. Shweta abrak, Shweta patra abrak, you will get pearly luster. So typical metallic luster, best example is the pyrite. Then quartz, as I have shown, the vitreous nature, water-like appearance. Then earthy, non-metallic hematite, or even the Gairica is the best example of earthy variety. The pearly, non-metallic dull, we can say non-metallic dull variety, or we can call it as the pearly talc. The surface is just shines like a pearl. So these are some of the examples. Now we can have some pictures so that it will be clear for us. Looking like a polished metal. The metal just looks like a metal. And even in metallic and non-metallic, there will be submetallic luster. That is little bit dull in nature and which is usually possessed by the sulfate groups. For example, chalcopyrite, copper sulfate and all. So the metallic luster is very evident in the native elements. Even the chalcopyrite will show the metallic luster. So these are the this is the few examples for the metallic luster. So only native elements and pyrites, the sulfates. When you see any mineral with the metallic luster, just you have to find out between the native elements and the sulfate groups. Your confusion should be in these groups, not among the other groups. So that's how you can segregate or you can narrow down your understanding towards the identification of the minerals. Then here the non-metallic variety. So non-metallic luster, which is further broken down into different varieties, as I shown. There is a pearl-like appearance here. The lepidolite is one of the examples. Even the Patra Shvetabraka will give the pearl-like appearance. Then dull earthy variety, bauxite mineral, or even our Gairica, that will give the dull earthy variety. Then waxy, that is chirosphere, which will give the waxy variety. Then glassy or vitreous. This is the quartz we have shown earlier. Then we have adamantine. This is very, very important because diamond is having adamantine luster, even the topaz, but most evident adamantine luster will be seen in this diamonds. In the Kanyakumari Devasthanam, I think that is closer to you people, I think. In 2011 or 12, when we went in educational tour, our teacher used to show in Garbhagudi the idol. There is a nose stud, and this is made up of real diamond, and the face of the devata will be visible with the shine of that particular diamond nose stud. So we can appreciate when you visit into the Kanyakumari Devasthanam. So in UG times, when we went to educational tour, at that time we are fortunate enough to know the adamantine luster of the Devata. So that is one of the typical adamantine luster, because I have not seen diamond in my hand. So that is seen far away from around 50 meters, I think. We used to see the Devata around 50 meters distance will be there from sanctum to the visible part. So, and the silky variety, again, the silky luster is most common in the fibrous asbestos and all. And here is one of the examples for tremolite. The next property is the hardness. So hardness is very, very important because even though luster and color are not obvious properties, but hardness is definitive for a definite mineral. The hardness is definitive. Hence, it will give us in proper diagnosis. As we show Vyavachedaka Nidana, for different classification, we will identify 2-3 diseases, and at the end, we will Vyadhi Nishchaya. In the same way, the minerals also identified by color and luster, you will come into the small group or taper down, but in hardness, almost we make sure that this material is 90% belongs to this mineral, because the hardness is fixed for the different materials. And usually for the assessment of hardness, we will use there is a scale, the Mohs hardness scale. There is a standard scale which is been developed for the identification of the hardness of the minerals, and which is having the different minerals which are having a definitive measured hardness from ranging from 1 to 10. And before going to the actual hardness scale, some of the common things which we have and what is the hardness of that. For example, our fingernail is having the hardness of 2.5, and our copper nail, what we put in our walls and all to hang the photos and all, that is around 3. And glass plate, the chemical glass plate, that is having the hardness of 5.5. Then steel nail, the copper nail is 3, and steel nail which is having the hardness of 6.5. And the porcelain plate, or we also called it as a streak plate. Usually we have kits for identification of the minerals. And for streak, we will keep two types of the porcelain plate. One is the black one, another one is the white one, because usually the silicates will not give any streaks. Silicate minerals, whatever seen, the monosilicates, cyclosilicates, those things usually they will not give the streak, and usually they will have white streak. For that, sometimes we need a black porcelain plate also. Then it is having the hardness of 7. By just scratching into it, we will know the color also, and apart from that, we will come to know the hardness also. For example, when you just take a gypsum in our hand, what will just we scratch with our fingernails, and even Dugdha Pashan or talk, just we scratch with our fingernails, because we know that our fingernail is 2.5, gypsum is having hardness of 2. So the gypsum usually scratched by our fingernails, and if your nails get damaged by that particular mineral, then you will sure that it is not a gypsum, it is having hardness more than 2.5, then you will not scratch that material. So like that, we can use different daily available things for the hardness also. Then coming to the Mohs hardness scales. So Mohs hardness scale is a material or minerals consisting of the 10 different minerals with known hardness, the definitive hardness. And these are the arranged in the 1 to 10. For example, for hardness 1, we have talc. Then for hardness 2, we have gypsum. And for hardness 3, we have calcite. And hardness 4, we have fluorite. Then apatite. Then orthoclase. Then quartz. Then topaz at 8. And then corundum. Initially, I showed the picture for ruby and all corundum. It is having the hardness of 9. Then we have hardest material on the earth, diamond, at 10. So this is how we have the Mohs hardness scale, and sometimes it's very we will remember first 2 and last 2, talc and gypsum, and the last corundum and diamond. The in between things we will usually get to forget when we used to ask our PG scholars about the what is the scale or what is the mineral for the 5th or 6th. They will not tell, because after some times they will forget. So that there is a code is available on to remember the scale. That is, 3 German captains found a French queen that can dance. So 3, that is talc, German, gypsum, captains, calcite, then found that is fluorite, that is apatite, then French, that is orthoclase and feldspar. The orthoclase is also having the 6 hardness, and the feldspar is also having the hardness 6. So some of the Mohs scale, they will use feldspar instead of orthoclase, because feldspar is more easily available. So you can put feldspar also. Then queen, that is for quartz, and that topaz, C for corundum, then D for dance. And then just you can remember this sentence: 3 German captains found a French queen that can dance, so that immediately you can remember the mineral which is having the particular hardness. So this is about the Mohs hardness scale. And one of the important information about the Mohs hardness scale is that this hardness scale is not a relative one. Because if you assume that the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, there is a gradual increase in the hardness of that material, that is wrong. Just these are having that particular hardness, but when you measure into the actual hardness scale, they will differ. For example, when you see the talc and gypsum, there is very little difference in the hardness. Then calcite, then again apatite, there is increase in the hardness. There is no relative increase in the hardness between the previous mineral and to the succeeding mineral. So you should not assume that the gypsum is having the double the hardness of the talc, and calcite is having the double the hardness or triple the hardness of the calcite, like that. There is no linearity in that hardness scale. So that we have to understand. And these are the materials. Talc we have, then gypsum, this is the material, godanti, then we have calcite, fluorite, apatite, feldspar. Feldspar will come again and again because of the group or Uparatna. This is the quartz, then topaz, then corundum, and diamond. So these are the some of the important points which we have to remember in understanding the hardness scale. And once we know that these materials are having this particular hardness, and whatever the material available, known material, that can be used to test the unknown material. Either, for example, I have the mineral of 5 hardness. If I got an unknown mineral, I want to test the hardness. Just I will take the hardness 5 material to and scratch it. If it scratches to the unknown material, then it is having the less hardness than that. And in reverse, if that unknown material scratches to the known mineral, then you should know that it is having a hardness more than 5. That's how we can understand or use the hardness scale to the elicit the hardness. So this is how the idea is that gypsum will scratch on tar, calcite will scratch on gypsum, like that. The previous mineral will be scratching on the succeeding mineral. That is how we can use the scratch test. Now, one of the next criteria for identification will be the streak. So, a streak is nothing but this is the true color of our mineral. So, true color of mineral. Then, how will you know the true color of anything? Usually, when first year students will get admit, first year PG scholars will admit into our department, and usually think we will discuss among faculty how are the students, and usually the thing is that the discussion come out that थोड़ा घिसने दो असली कलर बाहर आ जाएगा. तो थोड़ा काम करने के बाद ही पता चलेगा ना. द सेम थिंग्स अप्लाई टू द मिनरल्स आल्सो. व्हेन वी streak it into the material, then only come to know the true color of that particular mineral. So in a normal circumstances, you will not exhibit our true color. When you are put under pressure, then only we'll come to know what is our true color. We'll get angry, or we'll balance the work, or we'll take all the absorb the pressure, and we'll cope up into the mentor's words or not. In the same things applied to the minerals also. Minerals in their native way, they are the mask their colors because of the weathering and all. They are become dull and all. So when we streak and apply pressure, then they will exhibit the true colors. And this phenomena is important for us for identification of the particular mineral, because just only by looking into that, we will not identify which mineral is there and what is its true color. So that is all explained here. The streak is the color of the powder mineral. That is, the streak is nothing but the color of the mineral in its powder form. How it looks it in powder form, because in its the lump form, it will reflect differently. But when it's powdered, that will exhibit its true color. Then many minerals have different color when powdered and when they are in a massive form. So we will illustrate it by examples. By looking in as a whole mineral, they will look different. But when we rub it or when you powder them, they will look differently. And usually the non-silicate minerals typically leave a colored streak, whereas silicate minerals typically have white streak, as we have already explained. The silicates they are not having any streak. That means they will leave a white streak. And if you take a silicate group of mineral and you're having the white streak plate and go on scratching, it will just, if hardness is more than 7, it will just scratch. They will not give any streak. So for that, we need to have a black streak plate. So that is how the streak is important. So look into these two things, or these two minerals. So they look exactly different. The left one is looking a little bit grayish or black in color, and the right one is looking red color. The right one mineral is giving same color streak, but the left one it is not giving the same color streak. It looks different and giving the streak differently. That is how the streak is very, very important. And some of the important streaks which are defined are here. I have given some example. For example, our so the chalcopyrite. How chalcopyrite looks? It looks like a gold. And when in mining, if you found something yellowish, glowing, because it is having the metallic luster, it comes under the sulfate group. And when you usually find, and it looks like gold. But the thing is that just you streak it, it will give the black streak. So that's how you come to know it is not a gold, because gold will give yellow streak. Then how we can differentiate? The gold will give yellow, both look same in a massive form, but the gold will give yellow streak, but the chalcopyrite will give the black streak. Then we have cinnabar, which will give red streak. Then we have this hematite, which is give the red brown streak. The orpiment, golden yellow streak. Then crocite, that is yellow streak. So based on these streaks are definitive, and by using this property, then you can just identify, or you can narrow down your confusion. For example, if you brought any mineral, if it is not yielding any streak or otherwise yielding a white streak, you will only narrow down, or you will only differentiate in between the silicate groups. That's how we can narrow down, and that's how we can use this phenomena for identification of the minerals. Next, we have cleavage. The cleavage and fracture are a little bit interrelated, because the cleavage and fracture both are the reaction of the mineral to the pressure. If the breaking happens in the particular planes or cleavage planes, that will yield a typical cleavages. So if it is break in between with the pressure, that will lead into fracture. So major difference between the cleavage and the fracture is cleavage is the easy separation of the minerals, because as we have discussed in the silicate group of minerals, how the internal silica tetrahedron is giving different structure, whether it is giving a phyllophyllate form, cyclosilicate form, and when there is a less bonding, and there will be easy separation. When there is a multiple oxygen atoms are binding and there is formation of the compact, then there is no chance for the proper cleavage. The sodium chloride that is having usually separable by the cubic cleavage. So there are different classifications. So based on how it breaks with the easy pressure, the cleavages are again classified into different types. I will not take much time to explain those things. Those who are interested, I will give the references at the end of the class and you can refer. One is the basal cleavage, that is layer-like or page book-like appearance. We can sheet-like, we can remove the sheets. When you look into the mica, it looks like a sheet, by that is called as basal cleavage, the single surface. We can have the cleavage plane. Then we have two directional cleavage at 90 degrees. The feldspar is the best example. The cleavage will break in two direction at 90 degrees. So that is feldspar. Then we have three directional, that is three cleavage planes, halite, that is salt, common salt. Then we have again 60 degrees to 120 degrees, calcite, the hornblende, and then four directional fluorite, and then six directional sphalerite. It is very difficult to imagine the just by the explanation. Just I will show some pictures, then you'll have some ideas. So this is basal cleavage, muscovite, and single plane, just layer by layer, the sheets of the pages like. Then we have 90 degrees feldspar. There are two surfaces, 90 degrees, that is giving the two directional cleavage. Then we have three directional cleavage, calcite. There are three cleavage planes. What you are looking into is three cleavage planes. Then the same calcite, three directions, so three cleavage planes, but not at 90 degrees. Typically, calcite is having not at 90 degrees, but the halite is having the cleavage at the 90 degrees. Then we have octahedral cleavages. As you see this diagram, you can see the octahedral arrangement of the or octahedral cleavage of the mineral. The fluorite is the best example for the fluorite. And with this exam, you'll a little bit have the more understand. The cleavage, the first cleavage, basal cleavage, there is only one surface. Next, we have the feldspar, the two cleavage planes. Then next we have the hornblende, again two cleavage planes, but it is not at 90 degrees. See, the angle here is 120 degrees. The angle is increased. This both feldspar and this hornblende looks similar, but the angle is increased here. Here it is exactly at 90 degrees, but here it is the 120 degrees. Then halite, again 90 degrees, but three cleavage planes. Then we have calcite. These are the two cleavage planes, but not at 90 degrees. Then we have the fluorite with octahedral cleavage. So once we know about the cleavage, that will also give some idea about the identification of the minerals, because just we are having the three cleavage planes, then you just go on identifying whether it is a halite mineral or not. That is how we can use the cleavage as the identification tool. Then we have fracture. The fracture is nothing but when we apply a pressure. When we apply any material is subjected for a pressure, it will break in one or the other way. The easily breakable part is the cleavage, and when we put a large pressure or more pressure, it will break in any way. So even the things break in a particular manner. That will also give some ideas about the identification of the minerals, even though they are getting fractured, but they will break in some or the other way in the most of the time. That also gives an idea about the identification of the mineral. For example, we have conchoidal fracture, splintery fracture, and uneven fractures. Even fractures, uneven fractures, conchoidal fracture, and splintery fractures. There are various other classifications also, but some of the important types I have highlighted here. So here the conchoidal fracture, there is no exact cleavage plane. There is a convexity in that cleavage plane. That is conchoidal fracture. Then we have uneven fracture. So this is the Hackley fracture. While explaining the native elements, I have told about remember the gold. It will come under again the fracture. Hackley fracture, which is torn like appearance. It is not, this image is not exactly mimicking the Hackley fracture, but anyhow it's torn like appearance. Then Ardi, Girimalla and all, there is no fracture plane, but it will separate like a mud-like structure. They will be separated in a muddy way. Then we have fibrous. The fibrous fracture, there will be fibers, then they will give a fibrous fracture. The fibers will be removed out. As like our sweet son papdi, In North India, the people will have a sweet called as son papdi, which is having the same fibrous-like appearance. When you separate this sweet, the usually students after passing they will come to give sweet son papdi, and they will do the fibrous fracture, and we will have, because we are not able to consume all the square of that fibrous son papdi. How the son papdi breaks, that gives the fibrous fracture. Then we have splintery fracture. Again, this splintery fracture is also sometimes interlinked with the fibrous fracture. The more silky fibers, it will go for fibrous, and if the fibers are little bit hardened or little bit rough, that will yield into the splintery fracture. Now the granular fracture, even our gandhaka and all, if they are formed lump, they will yield into the granular fracture. Then subconchodial fracture. There is no proper conchodial fracture. These are some of the examples for the fractures. Now, the most important part, or you can say one of the important property of the crystal identification is the crystal habits. Now, I request students to observe the next three pictures, what I will show here, and you can write down whatever the things you will observe by looking into those three pictures. Just one or two things like color or shape or something like that. So that will be the base for the next discussion. So can we start? So look into this picture. Whatever the things comes in your mind, just note down about the just shape of the material or shape of the mineral, how it is there, how it is looking. Just 1 or 2 points. Okay, can I go with the second picture? So look into this picture. Okay, then I will go with the third picture. Okay, then you have observed some of the things in these three pictures. So most thing is that what things you have observed, we will discuss it later. So the crystal habit is nothing but how the crystal is formed based on its chemical composition. So that is how crystal habit is usually formed. When we are discussing about the silicates, we are also explained about the formation of the crystal habit, why it is important to understand. But the basic structure of the silicates is very, very important, or minerals is very important to understand the habit. So crystal habit refers to the distinct external shape of a single crystal, external appearance of the single crystal or a group of crystals. Because the crystals are not like our children's, they are born singly, raised singly. But crystals are they have been born in group. So there may be single crystal, or in the group also the crystal habits will exist. So the next thing is that the habit is influenced by the crystal's crystallographic form. How the crystallographic form is there, that influences the habit, as I explained in the prismatic or topaz also, how the cyclosilicate is giving the pyramidal shape or the shape of the particular mineral, and even the growth conditions of the particular mineral, where it is grown, whether the space is available for that particular mineral or not, and other impurities, whether trace elements are present in or not. So based on that, the crystal habit will be different. So coming back to these three pictures, what you have seen earlier. The first picture you have seen is all the pictures are about the chords. All three pictures are chords. Examples are chords. The first one is the euhedral. Why euhedral? Because what is the euhedral? Euhedral variety is the typical crystal nature. It's not like that all the crystal will be available in the euhedral form. They are available in the euhedral form, or they are available in the subhedral form, or they are available in the anhedral form. So first picture, that is the chords, which is cylindrical, tapered ends, and the shaft is elongated. That is the typical crystal nature of the chords, how it should be. Hence, it comes under the euhedral nature of the crystal habit. It doesn't mean that all the chords are available in the euhedral form. If you see one example of chords, and if you try to understand or identify the minerals based on the one euhedral form, then it is very, very difficult. So the learners, we should see all the forms of all the minerals, even the euhedral form, then the subhedral form. See the second picture, this also chords. This is having same the crystal end, but shaft is missing here, because this crystal, while growth, the space is not available for that. So the end is stunted there. Again, the lateral it is growing. Anyway, it wants to grow, but space is not available. at that pocket, then hence it is not having that elongated shaft-like appearance, but it is subhedral form. It hangs short, sharp, and the typical tapered end of the cords. Then this comes under the subhedral form. Then the third variety, there is no shaft, there is no growth ends. There are grain-like appearance, multiple grain-like appearance adhered or clubbed in a compact mass. That is anhedral form. Even though it is a cords, the space is not available for it, whether it is cooled rapidly or immediately it has been cooled based on that grains are formed. So different mineral formation processes will influence on the crystal habit. Hence, the crystals, what we see, most of the times they are not available in euhedral form. Most of the times you'll get subhedral or anhedral forms, because euhedral forms, if they will keep it in museum. So that will not come to the market also. So the subhedral or anhedral varieties usually we will look into, we will see in the markets and other things. And if euhedral is available, that will be usually kept in the museums. So these are the crystal main classification of the minerals. So whenever you are defining or writing a description of the minerals, we will start with this is euhedral variety of so and so copper pyrite. This is an anhedral variety of so and so. This is an subhedral variety of so and so mineral. So that you can description will be started while defining or while writing about the description of the any mineral while any kept in the examinations. In examination, we will keep samples for identification. Just students will just write the mica. So that doesn't indicate just you are identified. Then you have to identify all the things in which form it is an euhedral variety of mica, whether it is a sorosilicate or phyllosilicate, and what will be its hardness and how it will be fractured. If all the things, if you remember and if you write it, and the teacher will come to know that he is mastering that identification of the minerals, there is no need to ask any questions regarding the identification of the minerals. So for that, we need to have this basic understanding about the crystal habit. So I will wind up in within 5 or 10 minutes, sir. And next crystal habit will be the acicular, that is needle-like appearance. One of the example is stibnite, and the base, which is looking white, that is not a stibnite, that is a cord. The cords. This is cords based on the above the surface of the cords. This stibnite is forming. Then we have arborescent. I have shown the native gold and native copper. They are having the arborescent crystal habit. The tree grown like such. When the seedling happens, the trees will grow. It will grow like tree-like appearance. That is called as arborescent variety. Then we have tuberous variety. When we cut section a particular mineral, it will gives like a nodule-like appearances. So agate is a very common example. We call it as akika, and then this is again this comes under the chalcedony. There is a large group called as chalcedony. Chalcedony, the banded chalcedonies are called as agate. The agate is also a subgroup of the cords. When the cords will not get an growth space, it will stunted growth, have the stunted growth, and outside there will be cavity, and different banded appearances will come on based on the different liquids, and again that will form the akika or agate based on the different mineral composition. So this is the nodular variety. You can see the nodular or tuberous variety, and based on that you can identify the akika. Then that is a concentric variety, amethyst. Again, this is a variety of cords. There is a circular ring aggregate inside the center. That is also how we can identify the amethyst. Then this is a fibrous crystallized, the asbestos. We can Kaushayashma in our drug asbestos, we can compare it to the Kaushayashma. That is one of the crystal habit. Again, this is the same like stone papadi, what I shown in the splintery fracture. So this is the fibrous nature of that particular mineral. Crystal habit will be fibrous. Again, the fracture will be splintery fracture, how it breaks. That is mainly because of the threads of the fibrous threads of the particular mineral. Then this is the foliated, micaceous or lamellar. Very obvious property in the mica, but the diagram which I have shown here, there is not mica. There is a hematite. There is one variety that is called as micaceous hematite. Even the hematite also comes in the form of leaf-like structure. That is called as micaceous hematite. So as we know all about the mica, hence I have kept another example of the lamellar variety or foliated variety. There is a leaf-like appearances that is called as micaceous or foliated or lamellar. This is a picture of the hematite, micaceous hematite. Then we have Hofer variety. Initially, and while explaining the halides, I have explained about the salt, common salt. So there is a crystal outside crystal growth like appearance. So you see here, the inside crystal is not growing, but outside crystal is growing. So there is forming a hopper like appearances. In our pulverizer and all, we have a hopper external outside that is called as hopper. So that's hopper like appearances. Usually it is formed by the halite. So by just looking into this hopper like appearance, you can identify this is the halite mineral. How this crystal habit will be helpful in identifying. Then we have rosette or lenticular appearances. So this is the crystal growth. This is the gypsum. This is gypsum. This is formed in the dried lake. Here you can see the water bodies. So water has been evaporated and this crystal has been formed. This is the gypsum, and anyhow its water is available, hence it's an anhydrous silicate. So the rose-like appearances, the leaves or the crystal units are formed like a rose-like appearance. Hence is this gypsum is also called as rose of desert. This is also named as the rose of desert. So it is a rose which you find in the deserts. Hence it is called as rosette or lenticular crystal habit. So one of the gypsum is the best example for that. Then we have amygdala like appearances, like embedded almonds. How the almonds are embedded in the fruits, like that appearance. This is the zircon. This is zircon which is embedded in the other material. This is the picture of the zircon. This is called as amygdala crystal habit. Then we have massive or compact. This is the cinnabar HGS. So massive compact form. All the Gaerica, cinnabar, all which are comes in the massive compact form. This is the crystal habit. Then we have prismatic appearances. Our emerald, Arksha. Emerald is the prismatic appearances, the cylindrical appearance. So there is a prismatic nature of that particular mineral. So these are all the in other types of the crystal habits. Again, the symmetric, asymmetric, and the compact form. There are so many varieties of crystal habits. I have not listed into all the things which are important for us. Our Rasadravyas I have combined. This is the combined dendritic appearance. Here we see native copper is having the dendritic appearance. Apart from that, we have reticulated form. Then the native cellular we have seen this in the gold also. Then mammillary form. In case some agates also form in the external, they will look into the mammillary form. Lamellar hematite. I have shown the picture. This is again the micaceous hematite, what I have shown previously, and tabular form. So these are the different crystal habits. So this ends the habit, and almost we end the theoretical lecture here. But in the same way, we have what we can collected some of the important minerals from different parts of the India and some different markets. And I will take this opportunity to show some of the mineral pictures what we have in our museum. Swarnamaksika copper pyrite. This is the obtained from Khetri mines. The copper which is having the different pictures. And I think sir have seen all the minerals exhibitions when sir visited AlIA Institute of Ayurveda, New Delhi, and the CME. So this is the Gaerica, as you shown, everybody knows. There's no. This is the Navasadra, which is available in the Karibali market. The lumps are coming in the cubic form also, and in the lamellar form also. These are coming ammonium chloride. And the Sirajatu, everybody knows. There's no need for an explanation. And this is the Godanti gypsum variety. Those all the scratches are also you can see. All the students will come and scratch with the nails, as it is having the less hardness. Then we have Saindav Lavan, so there is no need. Then we have Hartal or piment. Then we have Spatika, Raktavarna Spatika. Then we have Dugdha Pashan, the tak. It's having very soft layers also you can appreciate here. Then this is Akik. This is the typical banded Akik, Chalkidini. This sample we have in our department. Then this Akik also comes in various, this is Spatika, Shvetavarna Spatika. Then this is a Badarashma, the Badara fruits like appearance, Badarashma. So then this is the abraka. We have around 4 to 5 varieties of abraka. I have failed to show here in your picture. This is one of the variety. All the varieties like Shweta Krishna Pita Vajrabraka, what we can say. So all the varieties we have, I think sir has have seen all the varieties, different varieties of abraka, and we need to encourage students to elicit what are the chemical differences in all the varieties, and why the biotite or the Krishna Vajrabraka is said. Is it because of the presence of iron in the Krishna Vajrabraka, so that we are taking the Grahya one. So that type of interaction we have to do while discussing about the minerals, that is hematite or loha ores. Again, this is Orchalavana, that's quite important. This is one of the Nilanjana variety. So these are the different, some of the samples which you have shown. And as I discussed, the discussion points are same. The Grahya and Agrahya variety, why we need to consider one variety is grahya, one variety is agrahya, even though it is coming under the same silicate group. That discussion we have to do sometimes when we get a time, or when in the department when you are interacting with the faculty members. Then why there is a classification of Uttama, Madhyama and Adhama varieties of the Rasadravyas, whether it is only because of the its essential element present in that, or it has any other roles, or only it's because of the Dehavada, or any it has some significance in the Lohavada also. Even Pyrojaka and all are surprising to know that they are also used as a Rasabandhana drug. And I don't know why they are used as a Rasabandhana drug, but when we are reviewing the literature, I come to know that different drugs are having some or other relation with the mercury. This point of time, I don't know why, what is that relation, but somehow when we initiate the discussion, and some or the other students, they can take a research work and they can come with some of the relations. Then I discuss the trace elements in all the varieties, how it is significant. So these are the points we can discuss, and we can have some idea about the different minerals. And I hope this lecture might be some of use for all the students. And I would like to take this opportunity to thank Dr. Ramesh and Sir, Principal, Head of the Department, Rasashastra and Bhaishajya Kalpana, and Dr. Arun Mohanan, Sir, Professor, Department of Rasashastra, and Dr. Vineet D, Associate Professor, Department of Rasashastra, and Dr. Prajishnath, Sir, and who is the one who invited me and who gave me an opportunity to interact with you all people. Thank you so much, sir. And also Dr. Dhanya, yes, madam, for all the team, those who are working. And recently I heard that the Amrita School of Ayurveda is top 2 ranked college in throughout India. And this also gives me an immense happiness to interact with the scholars and the faculty members who are the topmost colleges under the throughout India, because getting the rank is not mainly dependent upon the infrastructure or mainly dependent upon the faculties. It is all about the students, how the students are performing outside the institute, that gives the rank to the college. And if the students are exceptionally performing outside the institute, that means the faculty, the infrastructure, the efforts they are taking, that definitely brought you people for a good crown in the institute. So I thank all the faculty members, or all the management committee of the Amrita School of Ayurveda, for providing me an opportunity. And I will take this opportunity to also thank our director, Dr. P.K. Prajapati sir, for constantly supporting and giving an academical encouragement for anything, and our HOD, Dr. Galib sir. And we have Dr. Pramod Yadav sir as associate professor, and we have other 2 senior colleagues, Dr. Chandrasekhar Jagtap sir and Swapnil Chaudhary sir, for all the discussions, and continuously giving an scientific insight, and always motivating to know more about the drugs. So thank you so much, sir. And this is the how we can conduct different examination or different exhibition of the whatever the things the student will bring from different parts. We will periodically arrange the mineral exhibitions, and student will come, they will look into the samples, they will examine, they will interact with the faculty, and every time it will be knowing more. Sometimes we'll understand something, and next time the entirely new aspects will be known. So that is how we can increase our knowledge about the mineral identification, because this is the very crucial, as we have stated in the introduction slide, because once we miss the proper identification, the whole process for efforts will be missed. So these are the references. I have referred this mineralogy books. I can recommend the students, that is this red mineralogy book, Concept, Descriptions and Determinations by Berry, Masson and Derich. So vast detailed explanation is there in this book, and you can keep it in a library also as a reference book, and that will be helpful to know about the more understanding of the crystal habits, its nature in different planes. So I have not included everything, because it will be again very vast, and we will lack interest in identifying the minerals, and we will skip that part and look into other subjects. So I added those, and but for reference book we can keep that book. Then Mineralogical Society of America, that is a website. The students can go through this website. Here they have provided the authentic mineral pictures also. Then how to identify, how to taper down your identification. For example, if you have got a material, look into the luster. Metallic, so go into this follow. Metallic, then do streak. The providing this streak, these are the one. And then go for hardness. Then you can identify this one. Then non-metallic, do cleavage. Do this. These are the some of the groups, and then so like that you can taper down and go for identification. That flowchart is available in this Mineralogical Society of America, and tables are also available for each group of minerals, silicate minerals, halide minerals, carbonate minerals, everything for the flowchart is also available. So that you can refer, and I have referred the Encyclopedia Britannica also for the material, and even the Wikipedia is also a good source of material. Even it is not considered as one of scientific material, hence are not quoted in the references, but some of the information I have referred the Wikipedia also. So I thank you one and all for providing me this opportunity, and I hope this will be of a little bit use and to understand, at least to know more about the minerals. Thank you so much, sir.
Thank you, sir. Thank you, sir, for this valuable and insightful session. We look forward for further more sessions from you.
Thank you so much. Thank you so much.
Thank you, sir. We expecting more classes from you from all Mr. Ayurveda. I already discussed with Garib, sir. Okay, sir. Thank you very much, sir.
Thank you, sir. We were all the faculties are very eager to have the interaction with the you people. Anytime we are ready to do whatever the things you feel required, and we are ready to do this. Thank you so much for the opportunity, and I'll thank everybody for patient listening. And if you have any questions and any doubts, you can put it or you can mail it. I have taken much time. And after when you start reading, you will have more questions rather than having the rapid questions. It will not give any proper idea. But when you start reading one or the other materials, why silicate minerals are combining with only one oxygen atom, why this is not combining with the two oxygen atom, that type of questions will come when you start reading. So that will give the more depth in discussion. So just start reading, have the discussion with the faculty members, or when we have the next interactive sessions, we will discuss those materials, because this is the basic. Just we start create an interest among the students. We have started the basic slides.